So in our previous video, we thought about the situation where we're fitting a straight line through some points. So we've observed these black dots here. These are our measurements, and we've observed them with some uncertainty. And we've proposed a model, our straight line. So in this case, we proposed this model that f of x and theta is this parameter theta multiplied by x. So theta is basically just controlling the gradient of this line. And crucially, we also proposed a noise model. So we've said that we've recognized there's uncertainty in our observations of the true process we're interested in. And we've represented, we've come up with a model to represent that uncertainty. So we've said that our ith observation, yi, is equal to the prediction made by the model plus this noise term, where epsilon is a random variable that's Gaussian and has variance sigma squared. So we used the noise model to write down our likelihood. We decided we had a zero mean unit variance prior. And so from that, we wrote down an expression for our posterior distribution over theta. So the probability that this parameter theta takes a particular value given that we've seen these measurements y. And so we said in the previous video, you can kind of finish here. You can then plug different values of theta into this equation to find out what's most probable, what this probability distribution looks like. But actually, this is kind of a special case because you can actually solve this closed form. So by that, I mean, you can take all this stuff and you can rearrange it to find that the posterior distribution over theta is actually Gaussian, and you can get closed form expressions for its mean and variance. Okay, so our posterior distribution here, we just know it up to a constant of proportionality. We know we have a product of lots of Gaussians here and a Gaussian here. So what we're going to end up with is something proportional to exponential function. And then everything inside here is going to be multiplied by -1/2. And all the stuff that goes into this bracket, I'll just write as phi. So we're just making our lives a bit easier, basically. In this case, phi is going to be, so we start off by including the terms in the likelihood. So we have 1 over the noise variance. So we'll have sigma to the -2. And then we'll end up with a summation from I equals 1 to n. And we've got here yi, and then minus our model. Our model is just theta times xi squared. And then to account for the prior, well, this is a unit variance Gaussian and zero mean. So actually we just end up with a plus theta squared. So all I've done is by writing this thing, it's just I'm just expanding all of these terms without having to write the exponential every single time. Right, so now we'll just expand the bracket there. So we still have a sigma to the -2, summation over I. We have a yi squared -2 theta xi yi plus theta squared xi squared plus theta squared. So now we're going to do something called completing the square. So what I mean is, if we can get phi, so remember that our posterior distribution is going to be this. If we can get phi into a form, some constant a times theta squared -2 times another constant b, theta, plus something else, some other constant. That's going to be really good for us because it means we can show that the posterior is Gaussian and we can derive its mean and variance. So that's because we can rearrange this. If we take a outside of these brackets, so we now have theta squared minus 2b divided by a times theta, still plus a constant. Then it's easy to show that we can rewrite this as being a times theta minus b over a squared plus constant. So that means that we'll end up with our distribution will look like an exponential of minus a over 2 times theta minus b over a squared, with some other constant here, but that's not a function of theta. So what it means is if we can get our equations into this form, then we know that a has to be basically the precision of this Gaussian, and that the mean has to be equal to b divided by a. So to complete the square for this problem, all we need to do is write down what's been multiplied by theta squared. So we have a theta squared, it's been multiplied by, we have a sigma to the minus 2. And what else do we have? We also have that's been multiplied by the summation over xi squared. And finally, because of the prior, we have a theta squared over there. So that's plus 1. So automatically we know that this has to be the precision, so the inverse variance of our posterior distribution. Likewise, we say, well, what's been multiplied by minus 2 theta? Okay, well, we have, again, a sigma to the minus 2. And then that's multiplied by the summation of xi yi. So the summation over I of xi yi. And then there's nothing else here. So that's plus a constant. So by completing the square, we now know that the posterior distribution is Gaussian, and that this is its precision. So we can now say, therefore, the probability of theta given y is a Gaussian distribution. Theta is the random variable, and let's say it's got mean mu star and variance sigma squared star. And we already know that because this is the precision, we know that theta star squared is going to be equal to this term to the power minus 1 and then the mean. So we'll just look back up here. So the mean is equal to b. So in our case, b is all this stuff. So we put that down there. And then we can also see that it's been multiplied by the, okay, in this case, the inverse precision. So it's multiplied by the variance, the posterior variance, which we already have. So we'll write that here. Right, so this is a convenient situation because we don't necessarily have to try and evaluate theta over different over different values. We don't have to evaluate its posterior probability over a range of different values. We automatically know that the posterior is Gaussian, and we have expressions for the mean and the variance. So does this make sense? Well, let's take this thing and we will, I'll just rewrite it down here so we can kind of scribble on it, basically. So first thing to ask ourselves is, I guess, what happens if we have no data at all? So if we have no data at all, then just as a reminder, this term has come from the prior. So this is our prior variance is equal to 1. So if we have no data at all this, we can think about that as all our x's and y's go to 0. So if our x's go to 0, this stuff disappears. So it means that the posterior variance is equal to 1, which is the same as the prior variance. So no data, the posterior variance is the same as the prior. Likewise, if all our x and y's go to 0, then the mean of the posterior will go to 0 as well, which is the same as the prior. So if we have no data at all, the prior is equal to the posterior. That's good. It's like a sanity check. That should obviously be the case. Then we can think, well, what if we had loads of data? So the more data we get, let's look at this variance term. So this is the variance of the posterior. And obviously the stuff here is to the power minus 1. So the larger this number is, the narrower the posterior is going to be. So we're adding a load of positive numbers here, these xi's. So if we get more and more data, what's going to happen is that this term is going to become, eventually more important than this term, than this 1 on the end. So basically this add 1 that we've got from the prior is going to make almost no difference compared to if we have lots and lots of positive numbers being summed together here. So what's going on? Well, two things. That means that the posterior is getting narrower. Okay, so in this case, the more data that arrives, the less uncertainty there will be in our estimate of theta. And again, perhaps that, that feels right. Also, as we've just said, the more data that arrives in this case, it means the less significant the prior variance is for this expression. So what we're showing is that the more data that arrives, that information that's contained in the data kind of dwarfs the prior. So essentially, the more data there is, the less you have to rely on the prior. It's not completely true all the time, but it is in this case. And again, it's kind of like a sanity check that this seems about right. So here we've derived for this particular problem a closed form solution for the posterior distribution over the parameter of a model. And we've used that to kind of analyze some things that happen when we have no data or lots of data. In general, we can't do this. We can't get closed form expressions for the posterior. Then there's a load of other tricks that we can play in those scenarios. So what we're going to do in the next video, I think, is we'll just take a kind of closer look at this and actually derive Bayes' theorem, so we know where it comes from.